Since the era of Tesla, wireless power transmission has been the holy grail of electronics. Technologies such as inductive charging have served as the foundation towards this wireless future. Our goal is to expand on these technologies by designing a system that not only transmits power, but also data through magnetic fields. Modulated electro-dynamic induction is the manifestation of our goal. To date, we've successfully designed and tested a prototype, decided our final product specifications, and have a final design nearly ready for implementation. When undertaking a semester project of this magnitude, organization is key. My primary role thus far has been serving as team administrator, keeping the team on pace with deadlines, making revisions and additions to our research paper, keeping track of team meetings and experimental data, and assisting in circuit testing have been my primary responsibilities.
So now I'm going to go in depth about our MEDI design. First we start off with our Arduino microcontroller, which then triggers 3 different oscillators depending on whether we want to send a 0, a 1, or just a power signal. These signals are then fed into our resonating coils, transmitter, receiving coil, which then is broken up into either just the power signal, or depending on either the filters pick up a specific oscillator, which is then fed into a microcontroller to dictate whether it's a 0, a 1, or if it was just our power signal going to the microcontroller.
Alright, so my primary focus has been working on the data path for our system, specifically the bandpass filters. In order to conserve energy, we decided to use a passive implementation. The circuit is relatively simple. However, at our frequency range, inductors don't function properly, so we need to use custom inductors, which we calculate using a variety of formulas. In particular, the microhenry inductor has been giving us a little bit of trouble. This is one of the prototypes.
Due to the passive filter implementation and the difficulties associated with it using inductors, the team started focusing on other methods of retrieving the data from the power signal. The method in which we're using as an alternative will be to use a mixer to drop the frequency of transmission down to a frequency that can be read by an Arduino system. After the mixer, we would use open source materials to perform a fast Fourier transform, allowing for digital signal processing and retrieving of the bits.
Once we have the hardware aspects of the design established, microcontrollers will be used for the encoding and decoding of the data to be transmitted. These controllers will then interface with whatever hardware we decide will best demonstrate the use cases we envision for this technology. Once we've established basic data transmissions, we can also look into implementing rudimentary error correction to make our communications more reliable.
So now I'm going to go over our early implementation of MEDI. First, we have the Arduino, which will then trigger our oscillators depending on the data being sent, which then goes out to our transmitting resonant coil. Over here you see our receiving resonant coil, which is then here filtered out depending on the data being sent. We will also have a power line that will be powering the Arduino, so no battery is needed. And now our final design implementations will be changing out these store-bought filters with hand-wound filters. These hand-wound filters are able to handle higher frequencies than the store-bought ones. Otherwise, these would drop out at 13 megahertz. Our hand wounds can go up to about 1 gig. Also, the coils will be planar coils instead of hand wound coils.